In this video, we talk about how the derivative can describe our function. So we already know our derivative f prime of x. These are some other notations that we will be using. So dy dx, df dx, d of f of x, so d dx of f of x, and then some other notation as well. But this always just comes down to the limit of our difference quotient. It's the slope of our secant, right, as the change in x approaches 0, as our h approaches 0. So what we're going to notice is that if f of x is increasing, that means our derivative is positive. If f of x is decreasing, that means our derivative is negative. So if we look at the graph below, you can notice here, we'll use green for increase, that from here to here, our graph is increasing, and then the graph is decreasing, and then it is increasing, and then it's decreasing. So with derivative, what that tells us, if it's increasing, that means our f prime is positive. And if it's decreasing, our f prime is negative. So on these regions, our derivative will come out negative here, and our derivative will come out negative here, and positive in the other regions. So the reason is this. Remember, the derivative is the slope of the tangent. So if you were to pick any point on this little green area, and we draw a tangent line, you can see that that slope is positive. So any part where the graph is increasing, the slope is positive of the tangent line. And then if you pick any point that's going down, you can see here the slope is negative. Even here, just pick any tangent in that area, it's negative. Same thing here. The slope is negative. So remember, this is a negative slope because we're going down, and this is a positive slope because it's going up. And so it looks like this. Here's our function in Desmos. And so if I hit play, you can see our dot's going up and our slope is positive. And then it gets up to the top, and that's a slope of 0. And then now it's going down, and you can see the slope is negative. 0. It's going up, and now the slope is negative. Doesn't exist. And then the slope is negative here. So as you go through each of these, you'll notice that situation's happening. So if the derivative is positive, we get an increasing, and if it's negative, we get it decreasing. So very nice and consistent. Now, if the derivative is 0, that means we have a horizontal tangent. So like right here, that's our horizontal tangent. That means our f prime is 0. And again, it makes sense because if you have a horizontal line, the slope is 0. So this would also be slope equals 0. Now, if we get an undefined for our derivative, that means we have a vertical tangent. So you can actually see that here. Right here is a vertical tangent. That's our slope equal to undefined. That's our f prime equals undefined. We're also going to have points where it just does not exist as well. So let's look at the graph and we'll see that again. So if you notice, if I bring this back, right there, that's 0, and that's the max point. And again, just think about it logically. If this is positive and this is negative, so if we went from positive 5 to negative 5, what number do we have to go through? 0. You have to go through 0. So if we had a slope of positive 5, and we have a slope of negative 5, then in order to go from 5 to negative 5, you have to go through 0. It just makes sense. And then we also get that undefined situation as well. So right here, you'll see it just disappear right when I see it's gone. And then we also have another point here where it doesn't exist as well. It just disappears. And that one just makes sense because remember, coming in from the left, we have a nice positive slope, and then coming in from the right, it's negative. They're not approaching the same value. Limit doesn't exist. So that's what we have. So those situations, so if our derivative comes out positive, that means our function is increasing at that point. If it comes out negative, our function is decreasing at that point. If it comes out 0, that means we have a horizontal tangent at that point. And if it comes out undefined, that means we have a vertical tangent at that point. All right, so let's apply this now. So all of this just comes from the limit as our h approaches 0 of our secant line. So here's our definition. A function f is differentiable at a if f prime of a exists. It is differentiable on an open interval ab if it is differentiable at every number on that interval. So what it's saying is f is differentiable at a if that derivative exists. So we have to think about this as what it is. With our limits, we're approaching from the left and the right. So when you see the limit as h approaches 0 of our difference quotient, you also have to think about it as h approaching 0 from the left and from the right. And they have to be approaching the same thing in order for it to exist. So we're going to be finding out where f prime of a exists. And so when you think about the piecewise function, we have our v, and you basically have two functions. You have your y equals x, your y equals negative x, and then you have your vertex 0, 0. So we're going to be looking at the left, that's the y equals negative x, and the right, the y equals x. And then we're going to focus on it at 0. Okay, so let's look at the one on the right. Or sorry, we're going to start with the greater than. Yeah, the one on the right. All right, so for the greater than, this is our f of x equals x. And so that's for when it is greater than 0, it's going to equal x. So if we take the limit as h approaches 0 of our f of x plus h minus f of x all over h, it'll tell us if it's differentiable because we'll get an answer. So we're using f of x equals x. So f of x plus h would be would be plugging that in, so we get x plus h. And we know our f of x is equal to x. So subtracting these two would give us x plus h minus x all over h, and again, the x's cancel. So we end up with h over h, which is 1. Perfect. So now the limit as h approaches 0 of our f of x plus h minus f of x, which is 1, is 1. So that means for this side we are getting something that is differentiable because f prime of a exists. So from 0 to infinity, it is differentiable. And then we also know because it's positive that it's positive, we know that it is increasing. And that makes sense. If you look at the greater than 0, our function is going up, it's increasing. So now let's look at it for less than 0. So the limit as h approaches 0 of f of x plus h minus f of x all over h. And again, our f of x here would be negative x because we are less than 0. So our f of x plus h is equal to negative x plus h, and our f of x is equal to negative x. So now if we find our difference quotient, those cancel, and we end up with negative x minus h minus x all over h. The x's cancel, and we end up with negative h over h, which is negative 1. So now if we do the limit as h approaches 0 of our f of x plus h minus f of x all over h, we end up with the limit as h approaches 0 of negative 1, which is negative 1. So from negative infinity to 0, it is differentiable because it exists, right? And it's negative, so that means it implies that it is decreasing. Now, why am I not doing the left and right is because I don't have to. We're actually getting a value here that the limit is approaching. But if I approach 0, 0 is right in the middle, and so you've got to look at it now coming in from the left and coming in from the right. So that's where this one comes into play. And so we're going to place this now right here, and we're going to take a look at it. So from the left, that was this one. This is h approaching 0 from the left. This is h approaching 0 from the right when we do these problems, right? So let me place those over here. This again would be h approaching 0 from the left. This is h approaching 0 from the right. So if we use the one on the right, we already know exactly what it's going to approach. The one on the right approaches 1. So the limit as h approaches 0 of our f of 0 plus h minus f of 0 over h, this would become negative 1. And if we do the positive, we know it's 1. Because remember, this is just an x. This is a variable here, and that's a variable here. So if we're coming in from the left of 0, that would just be 0 and 0. Still going to be negative 1. And this would just turn into a negative, and this would turn into a positive as we move them from left to right. So it's negative 1. And then you can even just see it. Coming in from the left, it's negative 1. Coming in from the right, it's positive 1, because that's our slope. The slope here is negative 1. The slope here is positive 1. And now you'll see that the limit as h approaches 0 of f of 0 plus h minus f of 0 over h does not exist. And so if f prime of a does not exist, it's not differentiable. So f prime of 0 does not exist, which means the function is not differentiable at 0. So f is not differentiable at 0. And there you go. So if the derivative exists, it's differentiable, and if it doesn't, it's not. And so you use the limits from the left and right to show that they do not approach the same thing, just like we've done with limits before, and you can show that it's not differentiable. So I hope that makes sense. This is everything for the basics of derivatives.